Hi everyone, welcome to EdXP. EdXP is a learning and assessment platform for students to learn and assess themselves outside of the classroom. Today I'll be talking about the topic of complex numbers, which is covered in the IBDP Mathematics AA, SL, and HL subjects. I'll be covering a total of 5 questions today, 3 from past paper questions, as well as 2 more from our EdXP platform. So let's jump right in. The first question comes from the May 2017 Time Zone 1 Paper 1, Question 2. We have 2 complex numbers. We have one in Cartesian form. Oh, the second one is also in Cartesian form. Okay, and we have a complex number W, which is Z1 divided by Z2. And part A says by expressing Z1 and Z2 in modulus argument form, write down. Okay, so in IB, write down means no calculation is required. Okay, so let's first express Z1 in modulus argument form. Quite straightforward. So Z1 is 1 plus root 3i. This is a paper 1 question, so no calculator is allowed. We have in Cartesian form 1 plus root 3i. Let's change it to modulus argument form. Okay, so the modulus of Z1 is the square root of 1 squared plus root 3 squared. So that will give me 2. Okay. And the argument of Z1. Okay. So the argument is always the angle that the complex number makes with the positive real axis over here, theta. Okay. So this will be equal to arctangent y over x. Okay. And from our special angles, we know that this is pi over 3, which means that Z1 can be expressed as 2ei pi over 3. Okay, and let's do it for Z2. Z2 is 1 plus root I. Okay, we can go a bit faster now. And the modulus of Z2 is root 2 using Pythagoras theorem. And the argument of Z2 is pi over 4. Okay. Arctangent 1 over 1 is 45 degrees. Okay, so Z2 can be expressed in this form, root 2 ei pi over 4. Okay, so when we take W, which is Z1 over Z2, we have 2 ei pi over 3 divided by root 2 ei pi over 4. Okay. I have a rule that I teach my students, MDAS. So for Z1 over Z2, we divide the modulus and so modulus divide argument, we subtract. So we have root 2 ei pi over 60 degrees minus 15 degrees. So that will be pi over 12. Okay, and that is the modulus and argument of W. The modulus is root 2. The argument is pi over 12. Okay, so I hope you got that. Let's move on to part B. Hopefully we have some space here. We want to find the smallest positive integer value of n such that W to the power of n is a real number. Okay, so what we're going to do now is we're going to take W, which is root 2 ei pi over 12, and we're going to power it to n. Okay, another important formula, so 1, 2, De Moivre's theorem. When I power a complex number, I power the modulus and I multiply to the argument. This is De Moivre's theorem, or some call it DMT. Okay, so we have root 2 power n. Okay, the modulus is root 2 power n. Ei n pi over 12. Okay, here's the important part. If we want W to the n to be a real number, then the imaginary part must go to 0. Okay, to separate out the real and imaginary parts, I use cis form. So I can convert polar form to cis form. I get cos n pi over 12 plus I sine n pi over 12. Okay, So very importantly, we want this term over here, let me highlight it, the imaginary component to be 0, okay? And from trigonometry, we know that sine 0, sine 180, sine 270, okay, are all zeros. Sine pi, minus pi, 2 pi, 3 pi, 4 pi, sine of all these give me 0. Therefore, n, okay, must be equal to 12, okay, or 24, or 36, okay, so on and so forth. But since we want the smallest positive value, the final answer will be n equals to 12. Okay, so I hope you got that first question. Let's move on to the second example. This came from the May 2017 Time Zone 2 Paper 1, question 11. So this is a section B question. Okay, a lot of marks. This question alone is 22 marks. So usually there will be 3 or 4 section B questions that have such high weightage. Okay, and usually they mix it with other topics. So let's have a look at this question. For part A, we want to solve 2 sine x plus 60 degrees. So this is obviously nothing to do with complex numbers yet. Okay. And this is just trigonometry, okay, which you should be very familiar with by now. And we want to solve it for values between 0 and 180 degrees. Since the angles are not the same, okay, I usually want to simplify it, okay, by applying an addition formula. So sine A plus B is sine A cos B plus cos A sine B. Okay, this will help me a lot. And special angles, so the value should simplify. Okay, and for cosine, we have cos A plus B is cos A cos B minus sine A sine B. This is the addition formula for trigonometry. Okay, so we can simplify this. 2 sine x cos 60 is a half. Sine 60 is root 3 over 2. And these are our special angles. Equals to cos 30 is root 3 over 2. And sine 30 is a half. Okay, so we can simplify this. We have sine x plus root 3 cos x equals to root 3 over 2 cos x minus half sine x. Simplifying, I have 3 over 2 sine x equals to root 3 over 2 minus root 3, so that will be minus root 3 over 2 cos x. Okay. So this is all trigonometry so far. I can cancel out the 2's. Okay. And I can make tangent. So tangent x is equal to minus root 3 over 3, which is actually minus 1 over root 3. Okay. So this is a special angle to solve for trigonometry. Basic angle, okay, is, let's stick to degrees here. Okay, so basic angle is 30 degrees. If I draw the cast diagram, since tangent is negative, it will be in the second and fourth quadrants. Okay, but we're only interested in the second quadrant. So x will be equal to 150 degrees. Okay, there's only one solution between 0 and 180 degrees. So I'm just going to write this down here. Okay. So the answer to A is 150 degrees. Okay. Let's have a look at part B. So importantly, for section B questions, they are usually all linked. So we may need part A later. Okay, we're not sure. But always keep part A and B in mind when doing part C. Okay. Part B, show that sine 105 plus cosine 105 degrees is 1 over root 2. Okay, we can start from the left-hand side. Okay, show questions. Show left to right or right to left. So left-hand side is sine 105 degrees. I don't like it, but we can change it to two special angles. Sine 60 plus 45, right? That's 105. And these are our special angles. okay, plus cos 60. Again, I want to change it to special angles. This is a paper one, okay, so we cannot rely on our GDC. Sin A plus B is sin A cos B plus cos A sin B. And cos A plus B is cos minus sin. Okay? Sin 45. And these are special angles. Sin 60 is root 3 over 2. Cos 45 is 1 over root 2 plus cos 60 is half. Sin 45 is 1 over root 2. So we can simplify. So you need to know all your special angles very well to do this question. Yeah. Sin 60 is root 3 over 2. Sin 45 is 1 over root 2. Okay, let's see if we can cancel anything out. So we have, if we look over here, we can actually strike off the first term and the last term. Same thing. And then we have half of 1 over root 2 plus half of 1 over root 2. So that's 1 over root 2. Okay, so that would be the right hand side. And there we have shown part B. Okay, so A and B is done. Okay, so let's now move on to part C, which is our topic of interest, complex numbers. And this part C is worth 14 marks. So let's have a look at this. We have Z as a complex number, 1 minus cos 2 theta minus I sine 2 theta. So take note, the first thing you should know is that we have the real part here, which is 1 minus cos 2 theta. And we also have the imaginary part, which is negative sine 2 theta. This is very important. Okay, so to find the modulus, let's try the modulus of Z. We employ the Pythagoras theorem to find the length of the complex number. So we have 1 minus cos 2 theta. So the real part squared plus the imaginary part squared. Okay, I ignore the negative there because it just simply becomes positive after squaring. Okay, let's try to simplify. 1 minus 2 cos 2 theta plus cos squared 2 theta plus sine squared 2 theta. And we know from trigo identities that this is 1, okay, which simplifies. Okay, I can even take out the root 2. Right? I can take out the root 2 over here, and I'm left with the square root of 1 minus cos 2 theta. This looks very familiar. Okay, so if I were to employ the double angle formula, cos 2 theta is 1 minus 2 sine squared theta. Okay, sine squared theta, 2 sine squared theta is 1 minus cos 2 theta, which is what I want, which means that this becomes square root 2 and square root of 2 sine squared theta. Okay, and this simplifies to 2 sine theta. That is the modulus of Z. As simple as it gets. Okay, let's try finding the argument of Z. So the argument of Z, we can try to take the arctangent of y over x, so that will be negative sine 2 theta over 1 minus cos 2 theta. Okay, can we simplify this? So arctangent, what can we do here? We have two angles that are the same. Maybe we can change them to the same, maybe we can simplify the double angle. So we have minus 2 sine theta cos theta divided by 2 sine squared theta. Okay, double angle formula. Can we cancel out sine theta? Yes, we can. 2 and 2 is gone as well. So we have arctangent of negative cot theta. Very interesting. Okay. We want to find the argument of Z, okay, which will be the negative arctangent. Okay, so the next step will be to simplify. Arctangent minus cotangent theta is actually tangent of pi over 2 minus theta. Yeah, you can use a right angled triangle to see this. Okay, and then we can take out the negative. So arctangent, tangent cancels out, and we are left with pi over 2 minus theta. Okay, so alpha will be equal to theta minus pi over 2. Okay, so to find the cube roots of z, we take z to the 1/3. Okay, which means that, let's write z down first. So z is 2 sine theta ei of my argument. Okay, power 1/3. Okay, and using De Moivre's theorem, we power the modulus. Okay, this is paper 1, so we can't really solve the actual values. We have to put it in probably exact form, because there's no way we can find the exact values without GDC. Okay, so this will be ei. The argument here will be theta minus pi over 2 plus 2k pi, okay, solving for roots, and divide by 3. Okay, so we power the 1/3 into the argument. Okay, we multiply 1/3 to the argument when we use De Moivre's theorem. So this will be the final answer. Okay, I'll move on to our third example, also from the past papers. So question 3 or 7 came from the May, quite recently, the May 2021 Time Zone 1, Paper 1, question 7. Okay, so this is an 8-mark question. We have a quartic equation, so power 4. Okay, and z are elements of complex numbers. So the z values will have some complex numbers in there. We have 2 roots given to us. The first one is a plus bi, and the second one is b plus ai. Okay. Very importantly, we have to understand that if the coefficients of the entire polynomial are real, okay, then we can apply the complex conjugate theorem, okay, which says that if a plus bi is a root, then a minus bi is also a root, okay, the complex conjugate. If b plus ai is a root, b minus ai is also a root. So we can only apply the complex conjugate theorem if all the coefficients of the polynomial are real. Okay, so there I have the 4 roots, okay, but we want to find the value of a. Okay, when we encounter such questions, I always like to express the entire polynomial as factors. Okay, so since we have 4 roots, right, I can actually express them as vectors. So z minus a plus bi, like how you would normally express for real roots. Okay, the trick here is really, a lot of students make careless mistakes when there's a sign change. So we just got to be careful here. So z minus a plus bi, z minus a minus bi, z minus b plus ai times z minus b minus ai. Okay, quite a few plus and minuses there, but let's try. So let's expand this out. We have z minus a minus bi, z minus a plus bi times z minus b minus ai times z minus b plus ai. Okay, and usually when you multiply the 2 pairs together, you get a simplified real equation. Okay, let me show you what I mean. So if we expand out the first 2 terms, we have z squared minus az plus biz minus az plus a squared minus abi. Okay, we have a total of 9 terms, so minus biz plus abi minus plus b squared. Okay, so this will be the first part. And we multiply it with the second part, which is z squared minus zb plus aiz minus ZB plus B squared minus AIB minus AIZ plus AIB plus A squared. Okay, so make sure you have 9 terms. 1, 2, 3, 4, 5, 6, 7, 9. 1, 2, 3, 4, 5, 6, 7. Okay, and let's see what we can strike out here. Anything to simplify. Okay, so we have minus ABI plus ABI plus BIZ minus BIZ. Okay. And we also have Z squared minus AZ. Okay, so we are left with a very simple real equation. Z squared minus 2AZ plus A squared plus B squared. And for the second expression, can we cancel out anything? Plus AIB minus AIB plus AIZ minus AIZ. Okay, and we are left with, there's no more imaginary components, so it's all real. We have Z squared minus 2ZB plus A squared plus B squared. Okay, and there we have the expression. Should we expand out one more time? Yes, we probably can. Okay, this is for 8 marks. So we have Z4 minus 2Z cubed B plus Z squared A squared plus B squared Z squared minus 2AZ cubed plus 4A Z squared B See, at this point, it will be very tempting to expand out everything, but let's not do that because there'll be too many terms, a total of 16 terms. Okay, if we want to find the possible values of A, and we look at this expression, we know that Z power 4 is not very useful because we know the coefficient is 1. Okay, so maybe we can try taking Z cubed. If we investigate and compare coefficients of Z cubed, okay, so Z squared will multiply with minus 2ZB, minus 2AZ will multiply with Z squared. Okay, so that will give me minus 2A minus 2B equals to 4 over here. Okay, that'll be the first equation. Probably need one more for 2 unknowns, maybe the constant. If we take Z power 0, then we know that A squared plus B squared all squared must equal to 400. Okay, which means that A squared plus B squared must be equal to 20. Okay, we reject minus 20 because it has to be positive. Okay, and then if we solve these two equations, equation 1 and equation 2, simultaneous equations, A will be equal to 2 or negative 4. Okay, I hope you got that. I'll move on to some of our complex number questions from our platform. Feel free to try them out. You can log in and find our website at edxp.com. Okay, so this is for complex numbers. This is one of the questions in our database, so let's have a look. Find the values of theta for Z equals to 3 cis theta to be purely imaginary. So we've already done this just now in question 1. Okay, Z equals to 3 cis theta. Okay, if I were to show this very clearly, it's 3 cos theta plus I sine theta. Okay, always remember that this is the real part and this is the imaginary part. For this to be purely imaginary, the real part of the complex number must equal to 0. So 3 cos theta must equal to 0. Okay? And we know that the cosine graph looks something like this. And all the zeros occur at pi over 2, 3 pi over 2, so on and so forth. Yes? So I believe for this complex number to be purely imaginary, theta must equal to pi over 2. The cos 90 is 0. So the answer is A. But if we were to actually extend it in the negative region, negative pi over 2 is also 0. Okay? Pi will not be an answer. Okay, pi has a value of negative 1. So we have pi over 2, negative pi over 2, both. So the answer is D. I'll move on to our last example, also from our EdXP database. We want to find the argument of the complex conjugate, z star, if z is equal to 3 cis pi over 4. Okay, we know that if I do the argand plot, that this complex number has to lie in the first quadrant, okay, which means that the complex conjugate lies in the fourth quadrant, and the argument has to be minus pi over 4. So the answer is B, and this is for 1 mark, just to test your understanding. So we've come to the end of the complex numbers video. Feel free to explore our other videos and learn more about IBDP Math, and to try some of our EdXP questions online. Thank you.